Hi, welcome to AB Video 2.3D Part 1, more on tangent lines with product and quotient rules. Okay, so here's number 74. Find the points at which the function f of x equals x squared over x squared plus 1 has a horizontal tangent line. So, of course, we're going to be dealing with the quotient rule. Horizontal tangent line means that the derivative is 0. The slope of the tangent line is 0. The derivative here, we use a quotient rule. Now you're going to see the reason you're going to want to be factoring. So you'll notice even before I distribute, I see that I have a common factor of 2x. So 2x times x squared plus 1 minus x squared. The x squares cancel, and you're left with just 2x over x squared plus 1, all squared. And then you set that equal to 0, solve for x, and you get that x equals 0. You now know that the point of tangency is 0, comma. Remember, you're plugging that back into the original function f of x. And when you plug it back in, you will get 0. So, and remember, a fraction is equal to 0 when the numerator is equal to 0. The fraction does not exist when the denominator equals 0. Okay. Next, we have number 78. Find the equations, obviously there might be more than one, of the tangent lines to the graph of f of x equals x over x minus 1 that pass through, not at the point. This is not the point of tangency. It's just that your lines, both of them, pass through that point, negative 1, 5. And then they ask you to graph the function and the tangent lines. Okay, so for this equation, the equation they're giving you, of course, is y equals x over x minus 1. We're going to need a point and a slope. So the slope is going to come from the derivative of this function. Here's the quotient rule. So here's the derivative. And you now know that's the slope of the line. But you don't have a point of tangency, but what you do know, and I've kind of drawn these two lines, the equation y equals x over x minus 1 has a vertical asymptote, of course, of x equals 1, and a horizontal asymptote of y equals 1 as well. Anyways, so there's a point here, negative 1, 5, and I'm drawing two lines, each of which are tangent to the green curve and also pass through that point, negative 1, 5. So another name for the slope of the tangent line, besides the derivative, which we just found, is that if I pick a point on either a curve, the point of tangency, so it's on the curve and it's on the line, and I call that the point xy, then the slope of that line is the slope between these 2 points, which is y minus 5 over x plus 1. So I end up with this equation. However, I now have two unknowns, so I have to replace y by what it's equal to. Well, of course, that point xy that we took is sitting on this curve, and y, of course, is equal to x over x minus 1. And then at this point in time, feel free to use your calculator to solve the equation. It's doable by hand. It would just take a long time. So you get that x equals a half or x equals 2. What you've just found out is where these 2 points of tangency are. This is the one where x equals 2. This is the one where x equals a half. You then plug those x coordinates into the original function, and you will get these 2 points. And then for as far as the slope goes, the slope of the tangent line, of course, we had found by the derivative, found it equal to this expression. So we plug in a half, we get the slope of negative 4. But if we plug 2 into here, we get the slope of negative 1. And then there's the equations of your 2 lines. You could, of course, use the point negative 1, 5 for each one. And then the slope of the tangent line, of course, you could find using either formulas up there. And you'll notice that these equations look different, but in effect, for example, if I expanded this one, isolated y, put it in slope-intercept form, I get the same thing as if doing it this way. And that's the end of video 2.3D, Part 1.